This is the 9th lecture for Chapter 1. The topic of the lecture is bifurcations. For these dynamical systems, the term bifurcation means any structural change in the pattern of equilibrium values as a certain parameter changes in the differential equation. In general, we had differential equations as first order because that's what we're doing in this chapter, and it was some function of t and y, but there were also parameters involved in these differential equations, which I'm going to call mu. For example, you might have dy by dt equals 10y squared plus 3y plus some parameter mu, and this is a constant, and we look at how that constant changes. And we look at two results of the changes in the parameter on the differential equation. We look at the number and the location of the equilibrium values and also their stability. We're going to use three tools from the previous lecture, so I'm going to list those now. So first we have to find the equilibrium values. To find those, we have to set the derivative equal to 0, and we look for the values of y that cause that first derivative to go to 0. And those will be our equilibrium values. Then we graph those values on a phase line. So these are values of y. Let's say there's two of them. So here's two equilibrium values. We place those on the phase line. Then we have to determine their stability. There's several ways to determine the stability, but in this lecture what we'll do is take that next derivative and evaluate it at each equilibrium value, and if it's positive, it's unstable. If it's negative, it's stable. If it's 0, it's semi-stable. For example, in this case, if we found this node, this equilibrium value, to be unstable, then we would draw arrows away from it. If we found this one to be stable, then the arrows will be pointing towards it. We repeat these phase lines for values of the parameter, and then we sort of connect the dots in a certain pattern. All the unstable ones are connected with dashed lines. The stable equilibrium are connected with solid lines, and that gives us the bifurcation pattern. So here are the names of the bifurcation patterns. There's a saddle node, and there's a case 1 and case 2 of saddle node, transcritical, and pitchfork. To demonstrate the pitchfork, we'll use this differential equation. dy by dt equals y squared plus mu, and mu is just the parameter. So for the first step, we have to find the equilibrium values. So y equilibrium are the values of y such that dy by dt, which is y equilibrium squared plus mu, equal to 0, and we're only going to look for real numbers. So y equilibrium is going to be plus or minus the square root of minus the parameter. If the parameter is less than 0, then all this is positive, and we can take the square root. In that case, we have two equilibrium values. If the parameter is 0, then the equilibrium value is 0. If the parameter is positive, there are no real solutions, so we say there's no real roots. So we have two roots here, one here, and none here. Now here are the phase diagrams. These already have arrows on them, so sort of ignore the arrows for right now. So we have equilibrium values. In this case, parameter was about minus 5.5. So that's the square root up there. Here's when the parameter was minus 4, we're graphing these, we line them up along an axis of the parameters. So here's the parameter value of 0, and there was 1. As the parameter is negative, we have 2, plus or minus the square root of the absolute value of the parameter. So for example, right here, the parameter was minus 4, the equilibrium values were plus or minus 2. So that's graphed right here, and we just continue that. Now we'll go look at the stability of these values. So again, to find the stability, we look at the differential equation and we take its derivative with respect to y. In this case, the answer is 2y. Then we evaluate it at the equilibrium values. So let's look here first. If the equilibrium value is 0, then this derivative is also 0. That means this equilibrium value is semi-stable. Now for the other case, where there were two roots, we can evaluate it at the positive root and the negative root. It'll end up looking like this. So at the positive root, the derivative is positive. That makes it unstable. At the negative root, the derivative is also negative. That makes it a stable root. And now we can go back to the bifurcation diagram and draw the arrows. So again, here's all those phase lines lined up along an axis based on the parameter. When the parameter is negative, there are two equilibrium values. For the parameter has a value of, when it has a value of minus 4, then you have an equilibrium at plus or minus 2. Right. The positive root here, these positive roots were unstable by that previous test. So you see the arrows are pointing away from them. The negative ones were stable, and you can see the arrows pointing toward those equilibrium values. Now in the next step of drawing the bifurcation diagram, we sort of forget the phase lines and just connect the dots of the equilibrium values. If they're unstable, we connect them with a dashed line. If they're stable, we connect them with a solid line. So up here, we're going to be going through here with a dashed line. We'll be coming through here with a solid line. Oh, yeah, and then here you can see the semi-stable one. You see, what's happening in the saddle node is these two equilibrium values are coalescing into one as a parameter goes from negative values to 0, and after that there are no real equilibrium values. So the semi-stable one here at mu equals 0 has arrows pointing up in this case. So here's a bifurcation diagram for the saddle node case 1. We have a semi-stable right here at the sort of the nose of it. Oops. All the equilibrium values up here are unstable. They're connected with a dash line. Here's the locus of stable equilibrium values, and they're connected with a solid line. So in the saddle node bifurcation, two equilibrium values coalesce into one semi-stable one. And that's the saddle node bifurcation. This is case 2 of a saddle node, and it has I'm using a similar differential equation. The previous differential equation for case 1 was y squared plus the parameter. Here it's going to be minus y squared plus the parameter, and the result will be a mirror in the plane of the shape of the saddle node, and also a mirror of the stability. So we repeat the process. First we have to find the equilibrium values by setting that first derivative equal to 0, and that's y squared equals, and because of the negative sign, this will be y squared equals mu equals the parameter. Now if the parameter is 0, we have one real root, or rather two equal real roots, and the equilibrium value is 0. That's similar to before. If the parameter is less than 0, there are no real roots because you'll be taking the square root of a negative number. If the parameter is greater than 0, then there are two distinct real roots. So this will allow us to draw a group of phase lines against the parameter. So this axis is the parameter. Here it's 0. In this case it's negative. There's no roots here. No equilibrium values here. At 0 there's 1. And here we can line up some phase lines on this axis. And add some equilibrium values. This is just demonstration here, not the exact values. So we have them plus or minus, plus and minus, plus and minus as we go along. So you can see that it's sort of a reflection of the, well, is a reflection of the case 1. But now we have to look at the stability, and the stability will be different. Now for stability, we start with the differential equation. We take its derivative with respect to y, and we get minus 2y. Then we evaluate this at the equilibrium values to see whether the equilibrium is stable, unstable, or semi-stable. For the case of 0 for the equilibrium value, this next derivative is also 0, so that one is semi-stable. For the case of the two distinct roots, we had the y equilibrium equals plus or minus the square root of mu. If you put that equilibrium value into that equation, you end up with another negative sign. So the plus root, the equilibrium value that's positive, will have a negative value for the derivative, and that will make that stable. Before that was unstable. If the y equilibrium is negative, the derivative, I should have written it that way, is positive, those are unstable. And now we can draw arrows on the phase lines, then connect the dots. And here's the result. This is saddle node case 2. We have one semi-stable equilibrium of y equals 0 when the parameter, in this case for this differential equation, happens to be 0. After that, it breaks into two equilibrium values. The positive one is stable in this case, and the negative one is unstable. Now, other differential equations may show the same pattern, but the parameter may have different values. Perhaps that semi-stable one occurs when the parameter has a value of minus 5. But the basic idea in the saddle node is that you have two equilibrium values that coalesce into one, after which there are no more as the parameter changes. Now we'll look at the transcritical bifurcation. This has a very different pattern from the saddle node. And the typical equation to describe a transcritical is something like this: minus y squared plus a parameter times y. So the first step is to find the equilibrium solutions, and those are the values of y such that dy by dt equals 0. So you can just factor this equation and you'll find the two equilibrium values. One is the equilibrium value is 0, and the other is equal to the parameter. This y equilibrium equals 0 occurs at all values of the parameter, so that's a straight horizontal line. And y equilibrium equal to the parameter is another straight line. It's just a line with a slope of mu. Now we're going to take the next derivative test again. So we took the differential equation and we took its derivative with respect to y and ended up with minus 2y plus the parameter. And we have to evaluate it at the equilibrium values. So if we evaluate it, we're at y equals 0, we end up with the derivative equal to the parameter. So if the parameter mu is negative, then this derivative is negative and that equilibrium is stable. Where the parameter is positive, the derivative is positive, and therefore along that equilibrium value it's unstable. Alright, it's a little hard to see here with just words, so what we have is a line right like this at y equals 0, and in this here it's semi-stable, here it is stable, so arrows are pointing toward it, all the points on this line. Over here they're pointing away from it, and right here it's semi-stable. Now if we look at the other derivative, then that's just a line with a slope of mu. Let me get a different color. And a line. Alright. Okay, we're looking at this equilibrium value, which is a slope in this case, not a point. And we find out that that next derivative, well, that should be a y. The next derivative is the negative of what the parameter value is. So when the parameter is negative, this turns out to be positive. And the stability is reversed from the previous example, from this previous equilibrium value. So again, we're graphing this against the parameter. And if we drew the phase lines, for example, if we drew a phase line here, we would have an equilibrium at y equals 0 and another equilibrium up here. And this one is stable. The arrows would point toward it, and this one, they'd be pointing away. If we drew the phase line down here, we would have these two equilibrium values. This one is stable, and this one is unstable. But without the phase lines, here is your bifurcation diagram. This is the transcritical bifurcation. So we have these two straight lines. They cross at some value of the parameter, in this case 0, because of the differential equation. It doesn't have to be 0, but in this case it is 0. And not only do they cross, but the stability changes as where they cross, after they cross. The unstable becomes stable, and the stable becomes unstable. So this is the third pattern. It's called a pitchfork bifurcation. Now the typical example for this kind of bifurcation is a cubic, a differential equation that has a cubic in it, and you can factor out the one of the terms here. So the y is factored out here, and what is left in this case is exactly the same as the saddle. In this case, it's case 1. So from this, we have an equilibrium value, y equilibrium equal to 0, is independent of the parameter. It is a straight line on that bifurcation diagram. And then you have the two equilibrium solutions that are similar to the case 1, similar in their value, but not in their stability. The stability is different. So I'm not going to go through that analysis again. It's in the written lecture. The whole idea is that you take that derivative. You're going to take a derivative with respect to y of the differential equation dy by dt, and you find out where it's 0, it's semi-stable. If it turns out to be positive, it's unstable. If the value of this, when evaluated at the equilibrium values, is negative, it's stable. And then you connect the dots. So this dotted pattern is a saddle node pattern, but all of it's unstable. Then you have that extra equilibrium value, y equals 0, that's independent of the parameter, and that is a straight line right through here, but it changes its stability from stable to semi-stable to unstable right here. Okay, so this is the pitchfork, and the idea of the pitchfork, you can kind of see how it looks like a pitchfork. You have one, so there's one equilibrium here, turns into 3. For the saddle, 1 turned into 2. For the transcritical, 2 lines crossed each other, and all they did was cross and exchange stability. This is a subcritical pitchfork. The supercritical is the same, it's just a mirror image of this. So here's a supercritical pitchfork. The equation is similar to the subcritical, only there's an additional negative sign here. And when you factor it, you get case 2 for this saddle node, and you have the additional straight line y equals equilibrium equals 0. The stability is also changed. So it's outside of the pitchfork part, it's stable. So it's stable right here. Over here it becomes unstable. And the part that was sort of inherited from the saddle node is all stable. Okay, so let's recapitulate here. The idea on the bifurcation for these first order equations is that you're looking for changes in the number of equilibrium values and in their stability as some parameter in the differential equation changes. This parameter is some constant, and it's going to assume different values. For the examples that we gave here, they're pretty easy. They were like 0 value for the parameter, negative and positive, and when the parameter is negative, there was one set of equilibrium values and one set of stability. It went to a change at 0, and after that, when it was positive, there was another set. So that's basically the idea. First order equations, you're looking for a change in the number of equilibrium solutions and in their stability, and we did 3 cases. So here are the 3 cases. For the saddle node, you have 2 turning into 1, turning into 0, or going the other direction. You have 0 equilibrium values, you pick up 1, and that branches off into 2. For the transcritical, you have 2 straight lines that cross, and when they cross, their stability changes. For the pitchfork, you have 3 turning into 1, or 1 turning into 3. Again, these names are not given in the chapter 1 of the textbook. They're scattered in a later chapter, right? But I think it's good to put the names with them. It makes you kind of remember what they are. There's only one other bifurcation pattern called the hop bifurcation. It has to do, we won't talk about it here.